Okay, here we go. So, fasten your seatbelts. Today's going to be intense. We're going to do a lot of proofs and computation in today's class. We'll talk about determinants. Which are super important and can tell us a lot about matrices and the underlying functions they represent. And they will also form a hefty part of the equivalence theorem, which we're heading towards. So let's start that. This was in 2.1. Let's just recall how to find the determinants so we're all on the same page. I'll just do an illustration, 3 by 3. And suppose I wanted to expand along the second column for some reason. Maybe I happen to be the best one based on what these numbers are. How would I do that? What's the first thing I do, second thing I do?
Lay out your coefficients, which would be the entries in the column.
Okay, and what? Okay, so what's that going to happen? So I'm finding the determinant of this guy.
So you would have B times some matrix, and you could get that by the matrix that's left over from.
Well, no, there's something missing.
Really?
You label out plus or minuses.
You have to figure out the signs, right?
Right.
So these elements here will take a sign charge along the rows, and that's important. How do I get the signs? Yeah?
The negative 1 to the power of whatever the subscript of that element
Sure.
is.
So what's this going to be?
So that's going to be 1 comma 2. So it's negative 1 to the third power, so it's going to be a negative sign.
Right. Or you can know that positive is always the top left, and then it alternates everywhere else. So this is going to take a minus sign, then a plus sign, then a minus sign. So it's going to be a minus B times a matrix, plus E times another matrix, minus H times another matrix. And we are going to break it down to smaller matrices here. So what goes here? How do we figure this guy out?
So I had a question. The matrices is going to be 2 by 3s.
Which matrices?
The ones when you're solving for those.
No, you're always getting square matrices. So first of all, determinants are only defined for square matrices, and when you start breaking them down, the smaller ones are also going to be squared.
So that was going to be.
So this is a 3 by 3.
That was going to be D, F, G, I.
Right, how do you get that?
When you cover the second column, first row.
Right, so B is here. We block everyone out in his row and his column, and then we just write the matrix that's left over. That's going to be D, F, G, I, and do the same thing for E. Block out everyone in that row, that column. You'll see A, C, G, I, and do the same thing for H. Block out everyone in his row, his column, and you'll see A, C, D, F. And we can go even further here. How do you find the determinant of this? 2 by 2.
It's DI minus GF.
Right, so it's a cross multiplication and you subtract them. So that's DI minus GF plus AI minus CG minus AF minus CG. And you can expand and you can get a list of elements here. You'll see you're adding some terms and subtracting some terms, which is basically just an algorithm to figure out how to find the volume of the three-dimensional parallelepiped here. One thing you can also notice is that no matter what row or what column you expand it along, you realize that when you get to this point, it'll look exactly the same. You get exactly the same expression. So it's your choice who you expand along. You expand along the guy that's the easiest one. Another thing I want to mention is that some of you might know a method for finding determinants of 3 by 3s, which is like a shortcut. And the idea is you copy down the first 2 columns here. I don't know if you guys have seen this method before. A, D, G, E, H. And then you can take the cross, just multiply these terms down. So this is A, E, I, this is B, F, G, big friendly giant. This is CDH, right? And then you add all the terms here. And then if you go up along all the sequence of three numbers, you'd have GEC, and you take the negative of that, HFA, take the negative of that, and BDI, take the negative of that. You realize that when you look at this list, it's going to be the same as that list. I just want to emphasize here, this only works for 3x3s. Right, it won't work on bigger matrices. So this trick, if you know it, great, sure, you can use it, just know it only works on 3x3s. So if I give you a 4x4 determinant, you can't do something equivalent to this, it's not going to work. But this process that we described here will always work. In fact, this is how we define the determinant. Pick any row or column to expand along. First, figure out what signs each term should take. And so you're going to have each element in the row is going to be multiplied by its cofactor, which is just the determinant of the matrix obtained by blocking out its row and its column. And when you list all these together, you get a number. Geometrically, what that number is, it's the signed volume of the n-dimensional parallelepiped, but it will have other uses for us. We also saw that determinants showed up in systems of equations, and so they're useful in solving equations as well as many other things. Right, so that's just a recap of where we were so far. So today we're going to expand on this, because one thing we saw is that our choice of where to expand along was often determined by how the numbers looked in the determinant. You expand along the row or column that had the most zeros. But what if you don't have any zeros? What if everything is, all the numbers are kind of ugly? There are things we can do, and there are shortcuts to finding determinants, and that's what the bulk of this class is going to be about. How to find determinants more efficiently. Let's first get rid of some low-hanging fruit, shall we? Let's talk about determinants for something called triangular matrices. So there's a kind of matrix that we call upper triangular. If all entries below, come again?
Oh no, I'll just read it.
It's all entries below the main diagonal. Remember, that's the guy that goes from the top left to the bottom right. And by the way, this will go without saying if I forget to say it. Right, once we're talking about determinants, we're talking about square matrices, right? In this section. All matrices are square. It doesn't make sense to talk about the determinant of a non-square matrix. So now I'm going to define a certain type of square matrix that we're going to call upper triangular. All entries below the main diagonal are 0. So, example, 0, 7 is an example of an upper triangular matrix. You'll notice that you can draw a little upper right triangle here. Everyone below is 0. So that's an example of an upper triangular matrix. There's something called a lower triangular matrix, which has a similar definition. It's all entries above the main diagonal are all 0. Another definition. A n by n is called lower triangular. If all entries above the main diagonal are 0. That's a lower triangular matrix. See, any non-zero numbers that show up will show up in the lower triangular portion of the matrix. One thing I want you to note, diagonal matrices are both upper and lower triangular. Right, that follows from the definition of what a diagonal matrix is. Those are the guys where the only non-zero entries show up on the main diagonal. Zero. Okay. So here we have all our non-zero numbers are showing up here. There are zeros everywhere else. So you can think of it either as an upper triangular because all zeros are, all the entries below the main diagonal are zeros, or you can think of it as upper triangle because all entries above the main diagonal are zero. So there are times when I don't care if it's upper or lower triangular, it'll apply to any kind of triangular matrix, and so I can talk about just triangular matrices in general, because there are some things that will work with upper and lower and diagonals. It'll work for all of them at the same time, so as a category we can call them triangular matrices. Now let's talk about the determinant of a triangular matrix. So if you know a matrix is triangular, how do you find its determinant? Turns out there is a shortcut. How would you find the determinant of a triangular matrix? Yeah?
Just multiply the diagonal.
You basically just multiply it along the diagonal. Multiply all the diagonal entries, that's the determinant. So it's going to be A11, A22, all the way down to ANN, i.e. the product of the diagonal entries.
Is it because it basically forms like a rectangle or?
Yeah,
Or
the proof is easy. You can just tell the proof. Keep expanding along the top row. And you'll realize that you actually break down all the matrices until you get just a list of products. Right, so I can illustrate here. So let's add Right, so if I wanted the determinant of this, notice that it is upper triangular. Notice what would happen if I kept expanding along the first row. Right? Well, if I start expanding along, first column, although it won't matter, but first row would be like nice for the. I'm going to expand along the area with most zeros. It turns out that the first column for an upper triangle will always have the most zeros. It's the first row for lower triangles, right? So if I expand along this, none of these guys matter. I just have +1 times this guy. And then, now if I want to expand this, expand along the first column again. So it's going to be +2 times that guy, and +3 times that guy. Right, I'll literally have to be multiplying the guys all the way down, because they'll all break down, and because there are zeros always below it, I never have to compute all the smaller cofactors. Right, so I just end up multiplying straight across. And so right here, you're given that, and I see the determinant, you don't have to actually do any formulas or expand along here or something silly. You can just, oh, this times this times this times that, -30. Right? Expand along any row or column, and that's the answer you'll get. So triangular matrices are nice. The upshot is, in terms of determinants, we can turn any matrix into a triangular matrix. We're going to discover how to do that today. Or we can just create zeros whenever we want and maintain the determinant. That's what I'm going to teach you guys how to do. But we can just talk about the triangular determinant. Corollary here. The determinant of the identity matrix is 1. Because that's the guy where there are 1s on the main diagonal, 0s everywhere else. So any identity matrix, it doesn't matter what size it is, its determinant is going to be 1. Another way you can think of determinants in some contexts is as like a scaling factor of some sort. And so that's going to be useful. The identity function is not going to scale anything. It's just going to give you exactly what you have. And so it has geometrical meaning that the answer is 1 as well. So that's cool. Okay, so that ends this section. Let's move on to 2.2 and 2.3. I'm going to do these both at once. So it covers 2 things. I think we start out with using row reduction to find determinants. And we're going to follow up with talking about inverses, or inverse matrices. Here's some facts we're going to take on faith. One we can use as a lemma. If A n by n has 2 identical rows or columns, then determinant of A is 0. Any square matrix that has 2 identical rows or columns, the determinant would be 0. It's actually easy to see this with a 2 by 2, right? Because the determinant of that will be AB minus AB, which is 0, and you can use this as the base with induction to prove for larger cases. I'm not going to do it, but I can describe to you how you want to do it if you want to verify it yourself. So that's a nice little fact as well. So once you have an identical row or column, your determinant is 0. Geometrically, what this means basically is two of the vectors making up your parallelepiped are actually 1. So it collapses. Right? So let's say you have two vectors, like if you're in R3, you have two vectors in this plane, there's a third vector. Imagine that you take that vector and you collapse it on top of one. You now created something with volume 0. Right? So that's the geometric movement. Right? So whenever you have that, you will always have determinant 0. Because it means you have two vectors repeating. And it kills one dimension and completely collapses the volume. You can also have a corollary from this. Is that if A n by n has two proportional rows or columns, then in that case the determinant is 0. The idea is if you expand along one of these rows or columns, one of the proportional ones, the cofactor that you end up with would have the same entries. So that's why it's a corollary. But we're not going to prove that. So we have those two facts we'll prove. We have a bunch of proofs. I have to pick and choose which ones I want to show you guys. There are going to be a lot. Here's a lemma that we're going to want to prove. Alright, so we're going to build up some machinery and then we'll pretty soon be able to calculate determinants like experts. Okay, so lemma, here's an idea. Let A n by n, B n by n, C n by n be matrices such that all are identical. Except for one corresponding row. So they're all the same, except in, say, the third row, they're all different in that particular row, and they're different in a particular way. And in this row, the sum of rows in A and B gives the row in C. Then here's the conclusion. The determinant of C is going to be equal to the determinant of A plus the determinant of B. Which seems like a very strange fact, but it's going to be very useful for us. And geometrically what this means, it's kind of like you have a box where the volume of the whole thing is given by the determinant C, the volume of the first part is given by the determinant A, the volume of the second part is given by the determinant B. And summing these rows gives you the whole row of C. That's kind of what's going on geometrically. So if everything kind of lines up in this particular way where they're all the same in every dimension except this particular one, where in that dimension, the C is just the sum of the dimensions of A and B. Okay. That's just a 3D representation, but this works in general. Then it turns out that this will be true. The volume of C will be the volume of A and B. Let's prove this.
Hey, Professor, this is a question.
Yeah.
So, like, for that particular row, all of them are different, right? Is that what you're saying?
Yeah, just in that one row.
Okay.
To cut down on writing, I'll prove the 3x3 case, but larger cases are pretty similar. Right? 3 is complicated enough so the example isn't silly, but going larger than that, it's just more writing. Right? Doing the 2x2 case is just going to be extremely silly. It's not even going to, there's going to be no point to me showing it to you. But in 3x3, it's complicated enough for you to see the mechanism that's working, but it's not so large that I'm going to take forever to be writing down ellipses and these huge matrices. Okay? So let's say A is the matrix A, B, C, D, E, F, G, H, I. B is the matrix J, K, L, D, E, F, G, H, I. And C is, of course, this matrix. A plus J, B plus K, and C plus L. But it's the same everywhere else. GHI. So without loss of generality, remember what that means? That's just a phrase that you say when you want to prove it for a special case, but proving for any other case will actually be very similar. So without loss of generality, assume they differ in the first row. Right? So I'm taking the special case of 3x3s, and now I'm just assuming they are different in the first row, but they're the same everywhere else. Right? Exactly the same proof will work if they were different in the second row or the third row. You'll do exactly the same things, just the location of where you're doing it will change. Okay? So we're going to prove for the 3x3 case, we have these three matrices. I claim that the determinant of this guy is going to be equal to the determinant of this guy plus the determinant.
Just to be clear, we say without loss of generality for 3x3. Like this, they differ in the first order. That's the point of the fact that you can.
This is also without loss of generality, yeah.
Okay, so it applies to both. Okay. Okay.
So I can say without loss of generality, let's show for the 3x3, and without loss of generality there, let's just do it for the first row.
Okay.
Because the row is not going to matter. Just the algorithm or the set of computations is going to matter.
But likewise for the size of the matrix.
Mm-hmm.
Okay.
Okay. Now, let's look at the determinant of C in this case. What's going to happen? Here's how we're going to do it. We are going to expand along that row that's different. Right? So what would that look like?
Positive A plus J
So you have A plus J
times the determinant of EF HI
minus
B plus K. Determinant df gi plus c plus l determinant d e g h.
Okay. Do you see what we can do now? Are you seeing where we're going with this?
If we expand along the first row for both A and B, then you'll have,
Well, let's continue with this one. What can we do here?
Factor, I mean,
Well,
treat them
FOIL,
as-
we can multiply out, just expand, right? So what we have here is A times E F G H. Let's go over here, minus B times D F G I plus C times D E G H plus J times E F G H is plus minus K times D F G I plus L times D E G H, which is equal to what is this guy?
Determinant of A.
That's the determinant of A, right? This part here is the determinant of A, which I just took the first guy and expanded all these parentheses. That was actually the determinant of A. Plus, and this guy is the determinant of B by expanding along the first row. So that's true. Yeah, this is probably typical. Sometimes if there's something that's really annoying to like write it out, and like on a test, I'll just say, prove this theorem. It's true in general, but only prove it for the 3x3 case. Or only prove it for the 2x2 case. Because once I can see you know how to manipulate that, it's just expanding with ellipses to get larger cases, right? So if this were a 4x4, I would do exactly the same thing. I'll just have 4 cofactors instead of 3 cofactors. And exactly the same thing would happen. So it turns out that that statement is true. I do want, at this point, offer a warning though. Determinants do not distribute across sums, so that you need to be aware of. So if you're done writing that. It's just that if I have 3 determinants and they have this particular relationship, right? They're all the same except for one row, then the sum of these determinants is that determinant. But something like that isn't true in general. So let me just mention that before we move on quickly. Warning. The determinant of a sum, because you might be tempted to say this, is not the sum of the determinants in general. You can use a counterexample. Say A equals 1, 2, 3, 4. It's not hard to find a counterexample here, I don't think. But maybe it's negative. Right? So then the determinant of A plus B is just going to basically be the determinant of the 0 matrix, which we know is 0. However, but the determinant of A is equal to what? 4 minus 6, so it's minus 2. And that's actually the same as the determinant of B, right? Right? So if I add these two here, I get minus 4. On that side, I get 0. So it's not the same in general, so don't make that mistake. Determinant do not distribute.
Is
Yeah.
that supposed to be H and I for A and J?
H and I, where?
For
In
A
J.
and J,
Here? Yes. Okay. So we have this theorem now. This is true. Determinant of C will be determinants of A plus B in that particular relationship. Determinants do not distribute across sums in general. Now we can finally start to make things easier. Those are just some background that we needed.
Does
So
that
here's-
does that work for like if they're all positive entries though?
Come again?
And just curiosity, out of curiosity, like does that work for like just if they're all positive entries?
If what you're asking, is it possible to find determinants A and B such that that is true, the answer is yes. But it's not true for every combination of A and B that you can add. Right? So when we say not equal to something, in general, we mean you might have a few cases where it works, but it's not true in general. Right, so, okay, so here's determinant theorem 1. Now we're going to pull out the big guns now. The things that are going to help us actually get far more efficient at computing determinants. Let A n by n be a matrix. Let B be the n by n, be the matrix obtained. By performing a type 3 operation on A. Then the determinant of B will be exactly equal to the determinant of A. Basically what I just said, type 3 operations do not affect the determinant. Meaning if I have a matrix and I want to find its determinant, let's say I do a type 3 operation on that matrix first, then it turns out if I now find the determinant, I get exactly the same answer as I would have gotten if I didn't do it, right? I can take any matrix, do a bunch of type 3 operations, and the determinant will not change. The determinant will not be affected. I do want to mention that the type 3 here is as defined how I defined it, meaning you change a row by adding itself plus a multiple of some other row. Whenever you do such a thing to a matrix, you do not change its determinant. Its determinant will be unaffected by such an operation. Which means, if you can combine two rows in this way to create a 0, you're allowed to do it, and your determinant is not going to change. Proof. Again for the 3 by 3 case. So without loss of generality, a very similar thing will happen in larger cases. Assume without loss of generality, we do a type 3 in the top row. Meaning now my B is going to be, so let's say my A is going to be something like so if my A was something like A, B, C, D, E, F, G, H, I, then I'm going to do a type 3 operation between the first 2 rows, and it won't matter which 2 rows I pick, that's why without loss of generality. So my B will be this matrix. I'm going to change A by taking itself plus a multiple of another row. So A is going to be that guy, where R is the multiple of the row I'm taking. So I've now performed a type 3 operation in the top row with the second row. So replace the first row with itself plus a multiple of the second row, I would obtain a matrix that looks like this. Now, the determinant of B is going to be equal to what?
Do we want to expand along the first row?
No.
Okay.
I want to use something shorter, something more efficient. That's going to work very nicely in a larger context. And we can use the previous thing I proved. You see how to apply that? This is going to be the determinant of, it's going to be the sum of two determinants.
So the second matrix will have the first row be
What would the first matrix be?
A, B, C, D, E, F, G, H, I, R, D,
R, D,
R, E,
R, E, R, F, D, E, F, G, H, I, right? By previous lemma. Okay. One of these we know the determinant of.
Wait, sorry, is that like zeros on the bottom two rows or
No, there are no zeros.
the second?
These are arbitrary. A, B, C, D, E, F, G, H, I.
No, for
Do you see something that we know that we can use here, simplify things? Based on some facts I already gave you, maybe. Yeah.
Does the identical rows or columns, is that affected by a multiple?
We have something about the multiple. Remember that was a corollary of the identical?
Right, so the determinant of the second matrix is 0?
This guy here has determinant 0.
yeah, all
By
of
the
the
corollary. The two of the rows are proportional.
wait, you're saying the determinant of B is equal to determinant of A, that determinant plus who?
Yes. These two matrices are the same except for in the first row. This matrix is the same except for in the first row where it is actually the sum of the first rows here. So it applies to the theorem that I had before. So I can write the determinant of this as the determinant of that plus that. The determinant of this is 0 because it has two proportional rows, which we had by the corollary. And so this guy contributes nothing to the determinant. So we're just left with the determinant of this guy, which is determinant of the original.
Okay.
So type 3s don't affect the determinant. Yeah.
So geometrically, what happened? Do we just reorient our vectors or by doing the addition two rows by?
No, it's like you took two boxes and you stitched them together.
Oh. Yeah.
But the only reason you can stitch them together is because a bunch of sides are parallel. A bunch of sides are
Okay.
exactly the same vector. But it turns out when you stitch them together, one dimension of that is just going to be the sum of the two dimensions of the two original boxes. So we have that, that's true. Here's another thing. So the takeaway from that is one, it's a practice on learning how to write proofs, but two, it's to say that if you want to find a determinant of a matrix and it's ugly, and you can simplify it by doing a type 3 operation, you can do it and not worry about changing your determinant. If the determinant is what you care about, that will not affect it. Also, if that's the coefficient matrix for a system of equations, you can also do any row operation and not change the solution. So that's good. Determinants and solutions will not be affected by a type 3 operation. Other things will be affected, of course, but not the determinant. Here's another thing. Let A n by n be a matrix. If B n by n is obtained by multiplying a row of A. Could be row or column, but I'll talk about something later that's, anything I'm saying to do with rows will also apply to columns, because I'm going to say something about transpose later. By multiplying a row of A by K, then these obtained by multiplying a row of A by K, i.e. that was what we call a type 2 operation, right? That was our definition. Multiplying a row by a scalar is called a type 2 operation. Then, turns out the determinant of B is going to be equal to, it's going to scale the determinant of A by that same scale. i.e. type 2 operations scale your determinant. By the same scaling factor that you use in the operation. It's like you took a box and then you multiplied one length of the vector, one vector along the edge of that box by a number. It's going to stretch that box, and that's going to determine the volume. Right? So type 2 operations scale your determinant. So a type 3 won't have any effect whatsoever. A type 2 operation, though, it's going to scale it. The proof here is easy based on the definition of the determinant that we have. So we know expanding along the ith row, we get, right, so I is just some arbitrary row. We already have the formula for this. The determinant is going to be ai1 big C I1 plus AI2 big C I2 plus all the way down to AIN big C IN. This means the determinant of B also expanding along the ith row will now have what? A factor of k on all the terms, right? Because my A terms are all multiplied by k when I multiply the row through. That's going to be equal to KAI1 CI1 plus KAI2 CI2 plus KAIN CIN, which is just k times the determinant of it. Which means if you want to find the determinant of a matrix, and to make it easier, you multiply a row by 2 for whatever reason that might make it easier. It means that the answer, you'd have to divide it by 2 because you've actually scaled the answer when you do it. So you have to remember, oh, I did this thing, now I have to undo it for the final answer. Here's a corollary. think that would be?
Equals k times determinant A? No. N
Which-
times k.
When you say KA, what are you doing?
That's multiplying to every row.
Right, you're multiplying every row by K. Now, every time you multiply a row by K, what happens?
It scales up by a factor of k,
Okay, so what is that should
the
be?
number of rows.
Right.
That many
So it's
times.
K raised to the number of
Columns?
rows. Well, number of rows is the same as number of columns. It's gonna be squared times the determinant of A. Right? So example, if I told you, suppose A 4 by 4 is a matrix with determinant of A equals -2, find the determinant of, I don't know, 3A. And what would that be?
3 to 4.
It's just going to be 3 to the 4th times the determinant of A, which is going to be 3 to the 4th times -2. And that would be your answer. Now there are times on tests when I put a problem like this where I gave them a 4 by 4 matrix and said, find the determinant. And then in part B I said, find the determinant of 3 times that matrix. And people actually multiplied every row by 3 and went through that whole process again. No, there's a formula that does this. Right? And they're like, find the determinant of A inverse. And they're like, they find the inverse and then find that. There's also a formula for that as well. We'll get to all that. Like, find the determinant of A to the 10th power. They're multiplying A by itself 10 times. You didn't give us enough time, man. What are you talking about? That's a 2-second question. Okay. So it's a very nice property to have. So once you know the determinant of some base matrix, then multiply by any scalar, you'll know the determinant right away. That follows by this property. Here's a third theorem. About how a type 1 operation affects it. That A n by n be a matrix. And if B is obtained by swapping or interchanging 2 rows, i.e. a type 1 operation, then the determinant of B, does anyone know what swapping rows does?
Negate.
It actually negates the determinant. Right, it's kind of like you're switching orientation. But computationally, it's easy to see and not easy to see at the same time. Because I can tell you exactly how you can know that, but it might not be obvious to you why that would be the case. Proof. A type 1 operation is equivalent to doing several type 3 operations, which is not going to change the determinant. Followed by a type 2 with k equals -1. In other words, we can create an algorithm for swapping two rows that's precisely consists of doing this, right? Doing a bunch of type 3s is not going to change your determinant at all. In the end, when you multiply by that -1, the previous theorem tells us it's just going to scale our answer by -1, and you get this. To show you the algorithm, I'll illustrate the algorithm with you on a 2x2, so you can see what I'm talking about. Of course, the exact same principle I'm showing you here can be used without loss of generality. So let's say I have a matrix A, B, C, D. And what I want to do is interchange these two rows. I want to swap A, B, and C, D. What I can do is, I can do a type 1 in row 1. Take row 1 plus row 2, type 3. This is a type 3 operation. This gives me A plus C, B plus D. Leave that alone, right? Notice that here, determinant unchanged. Now what I can do is take A plus C, B plus D. Now what I'm going to do is I'm going to say, take row 2, the row I'm changing should not be scaled by anything, and I'm going to add to it -1 times row 1. What would that give me?
Negative A, negative B.
This gives me negative A, negative B. Again, this is a type 3, right? Determinant not changed. The third thing I'm going to do is I'm going to add these two. Take row 1 plus row 2. Again, it's a type 3, so the determinant is not going to change. If I add these two now, I get C and D up here, and here I get minus A minus B. Now to get this to be the top row, now I can just multiply that row by a -1. So this is row 2 times -1, and here's where my type 2 comes in. Right? So I did a bunch of type 3s, which doesn't change the determinant, and I have to finish it off by multiplication by a -1. Right? And that scales the determinant by a -1. So this algorithm can be done to interchange any two rows, right? I did it with a 2x2 with the first and second row, but I could have a 50x50 and choose the 15th row and the 17th row and do the same thing. Right? These are equivalent. So now we know how row operations affect determinants. Type 3s do not change the determinant. Type 1s negate the determinant. Type 2s scale the determinant. Okay, great. Do I want to give you any warnings at this point? I don't think so. Let me double check. No. Okay. So this leads to a method that we call pivotal condensation. Basically, using row operations to compute a determinant. You can create zeros where there are none. You can even make a matrix triangular if you want. Etc. Right? You can change the composition of your matrix using a bunch of row operations. Of course, remember when we're doing row echelon form, right? That's kind of what you're doing. You're trying to make something upper triangular, right? If it's square, the goal would be to attempt to get it to be upper triangular with a certain form, right? So you know that you can use row operations to do this, and now we know when we do each individual row operation how it affects the determinant. So my recommendation is to stick to type 3s, if at all possible. Because you don't have to change your answers. Right? Every time you swap a row, you have to remember, oh, I need to multiply my answer by -1. Every time you multiply a row by a scalar, you have to remember, oh, I need to divide my answer by that scalar. Right? So you have to keep track of what you're doing. If you do type 3s, though, you don't have to keep track of what you're doing. Nothing's going to change anyway. So let's do an example. So let's do this one. Nothing too fancy, just a 3 by 3 to illustrate what we're going to be doing. So you're faced with that, potentially something larger, like a 4 by 4 or 5 by 5. But now I'm going to change this guy using row operations in such a way that the determinant will change in a predictable way, and I'll be able to answer it. So pivotal condensation, that phrase comes from the fact that you can choose someone to be a pivot and then use row operations to make everyone else 0 in that row or column. So let's actually try that. Let's say I wanted to keep the first row, not doing anything. But let's say I wanted to make this guy 0. I just randomly picked. Okay, that's going to be my pivot. I just randomly picked that. You can pick anyone you want. Okay? So I'm going to want to create zeros in his column, which I don't currently have. So how can I get that here?
You could do row 2 times 2 and combine it with row 3 times. Row 2 times 3 combined with row 3 times 3.
That's not a type 3. Let's stick to type 3 if possible. You can do this with a type 3. I would take row 2 and do something like add to it -2 row 1. Right? So I want to change the second row, so that second row should not be scaled. Right? The basic type 3, the elementary row operation type 3, the guy you're changing does not change. You add to him a multiple of someone else. So I'm going to do that here. So I'm going to change row 2 by taking itself plus a multiple of someone else, in this case the first row. So I'm going to add this to -2 times that, which gives me 0. Add this to -2 times that. That's going to be what, -3? Add this.
3.
Yeah.
Oh, +3. Add this to -2 times that. Now I created a 0, and the determinant's not going to change. I just did a type 3. What about this one? I can leave row 3 alone and add to it a multiple of another row, say 3 times row 1. And that's not going to change the determinant because it's a type 3. So this plus 3 times that, 0. This plus 3 times that, -5. This plus 3 times that, 13. That's 13. So it turns out the determinant of this matrix is equal to the determinant of this matrix. Now they're not the same matrix, but in terms of determinants, the answer is going to be the same. And so now what I can do is expand along the first column. Right? Now I've created zeros where there were none. Right? And I could have gone even further. I could have made this a 0 and just do multiplication along the diagonal at that point. But because these two are so different, the 3 and the 5, they don't really have any common factors, I probably have to do some elaborate scheme in order to get those two to be the same. I'd have to incorporate using type 2s at that point, and then probably don't want to do that. But yeah, this is going to be now equal to, this is going to be a plus 1 times, block out everyone in that row and that column, 3 minus 7 minus 5, 13. And now that's just a 2 by 2, I can get to that answer easily. That's going to be what, 39 minus what, 35? Answer is 4. So that's just an illustration. And you can actually do it on this without creating any zeros, just brute force this one out. You realize that the answer is 4. Right, now this is an important idea, not just because it makes your life easier when you're writing things on a test, if I ask you to compute some large determinant, but even if you're using computers, you want to program tricks like this into your computer because calculations compound. And in practice, if you're using a computer to deal with matrices or linear algebra, chances are you're going to have thousands of rows, millions of rows. You're multiplying matrices and finding determinants. All those little operations, they add up, and they add up quickly. Right? So if you can do any shortcut where you can tell a computer, you don't have to do this huge calculation over here, you can instead do this operation and then do a smaller calculation, and a lot of times that's a lot better. And the programming, the computation time greatly decreases, the amount of processing power, the amount of cooling that you need greatly decreases. So these things are not only important for us, they're important for computers as well, knowing all these little tricks. And so that's where the theory comes in. So linear algebra, highly applicable, a highly applied mathematical science, but studying the theory, there is a lot of benefit to doing that. It helps you with the applied stuff. So this process is called pivotal condensation. That's what it's called. So you can use row operations to reduce your determinant to something more manageable. Just be aware of how each type of operation affects your determinant. So type 3s, no change. I don't have to worry about changing anything. If at any point I multiplied a row by a constant, I know that whatever answer I got here, I'd have to divide by that constant. If at any point I swap 2 rows, I have to take the negative of this answer, and you have to keep track of what you're doing. Okay, any questions?
So because we didn't swap any rows, it didn't affect the sign?
Yeah, I didn't swap any rows, I didn't multiply anyone by a constant. I didn't do a type 1 or a type 2, I only did type 3s. So I didn't have to worry about anything else. If at this point I randomly swap these 2 rows for some inexplicable reason, I would have gotten a -4 here, and then I have to remember to change it to the +4.
And the 2 and the 7 would switch signs also?
The what?
If you swap the rows that you're talking about, 2 and 7 would switch signs? Or no?
No, if I just swap these, I'll know just multiply the final answer by -4.
Okay.
Right. So every time you like swap it, you just make track of it. I need to multiply by a negative, right? You'd have to keep a tally of what you're doing. Okay. Some other determinant facts. Theorem, I believe we're on 4, that an by n, bn by n, the matrices. Then it turns out that the determinant of A times B, determinants actually distribute across products, which is pretty cool. That's the determinant of A times the determinant of B. Proof. Left to the reader. Have fun. Here, there's a nice corollary from that though, which I want to get to. And we'll use this to prove some other things when we get to inverses. Corollary from this theorem is that if you're finding the determinant, and this goes back to that question I mentioned earlier, of a matrix raised to a power, right? So like I gave you a matrix A and I'm like, find the determinant of A raised to the 100th power, right? Don't multiply that matrix out 100 times and then find the determinant. It turns out it will be, what will it be?
The determinant of A to the power of K.
Right, it's the determinant of A, and just take that and raise to the power of K. Right, because this guy is going to be just the determinant of A times itself, K times. And using induction on this guy with this formula, you can, this is just going to split into the determinant of A times the determinant of A times the determinant of A, and that happens K times. At this point, you'd employ induction. We'll do some induction proofs later, and I know I'm mentioning it, but we're not doing anything at this point. But yeah, and then that leads you to here. Okay, so let A be the matrix I just gave you. Find the determinant of minus 2A. Find the determinant of A to the 4th power. So, guess what we have to do here? We have to multiply each row by minus 2. Maybe we can do pivotal condensation. No. What's the answer?
Minus 8.
Minus
Right.
32.
Because we know what the answer here was, right? This is the same matrix we had before. Determinant of A was 4, I think we found. So this is going to be?
Minus 32.
How do you get that?
Negative 2 to the power of 3, because
Right.
it has
So you have,
to.
you have to raise it to the number of power of the rows times the determinant of the matrix. That becomes minus 8 times 4, which is minus 32. What about this one? Well, if we're going to multiply that by itself 4 times,
256.
which students have actually attempted to do. But no, this is just going to be the determinant of A, and you take that to the 4th. Which is just 4 to the 4th, which I'd accept that. Which at some point, I mean, for like the tests that we'll have, I think I'll allow scientific calculators, not the graphing ones, because the graphing ones can like do everything we're talking about, so I can't allow graphing ones. But if you have simple calculators and you don't want to worry about arithmetic, that's okay. Right, so once you know the determinant of a matrix, I can talk about determinants of algebraic operations on that matrix, and you should be able to get to the answer pretty easily. We don't have to actually compute all these things. Another theorem, let A n by n be a matrix. It turns out the determinant of A is exactly equal to the determinant of its transpose. Right? And by that reasoning, everything I said before that applies to rows when you're finding determinants will now also apply to columns, because in the transpose you interchange rows and columns. So the first row becomes the first column, second row becomes the second column, etc. Proof of this is just easy. Expanding along the ith row of A gives the same result as expanding along the ith column of A transpose. So find the determinant. This guy is like you tilt your head and you just found the determinant of the original. So I could do something like, for the above, I could ask you, oh, find the determinant of minus 2 A transpose. And you're like, oh my god, I have to find the transpose and then multiply by 2. Nope, it's the same answer. It's not going to change. Determinant of a transpose is the same as the determinant of the original. Now we're going to want to talk about some more things to do with determinants, but we're going to have to introduce inverses. So we're going to dip into 2.3 for a little bit. At this point I won't be able to tell you how to find an inverse, so I'll just tell you some facts about it and we'll do some computations with inverses next time. So let's say we have a square matrix. If, and this is a big if, meaning it might not exist. If there exists a matrix A, matrix B, such that if I take A and multiply by B, I get the identity. And conversely, it actually commutes. If I take B multiplied by A, I get the identity. Then A is said to be invertible. Or non-singular. And we call B its inverse. And we write this notation. A with a -1 power. Note, A to the -1 power does not mean 1 over A. It's a notation for the inverse of a matrix. Right, so it's kind of like when you see sine inverse, right? It does not mean 1 over sine, right? Right? 1 over sine is cosecant. It's not the same thing. It's just a notation, kind of, it comes from the inverse function, which I don't know why they made that. Well, I kind of know where that kind of comes from, but when it applies to other things, people get confused with the laws of exponents, but it's a notation, okay? So when I write a to the minus 1, it means a inverse. It means it is the matrix such that if I multiply by a on either side, the result will be the identity matrix. And the word inverse comes from the fact that it's the multiplicative inverse, right? In the sense that, this is in the sense that, say, a half is the multiplicative inverse of 2, right? Because if I take 2 times a half, I get 1, which is the identity for the real numbers. Which, when we're talking about real numbers, we call this the reciprocal. It's the same thing. And that's kind of where that minus 1 power came from, because this, in the real numbers notation, you can write that, and it means this. But in other notations, that's not what it means. Okay. Right, so it's taken to be a very general definition. You don't want to think of it in terms of division. It's not division, right? Division is by definition an operation that is defined on all non-zero elements of a set. It turns out that there are non-zero elements here where a matrix B does not exist that does this property. And so it's not wide among all matrices. This is just something that some square matrices have. Not all matrices have determinants. I have inverses. Not all square matrices. So don't assume an inverse always exists. Right? There are tons of examples I can give you. That guy has no inverse. There is no matrix you can find that when you multiply that, you get 1, 0, 0, 1. It's not going to happen. It's impossible. Okay. So this is the definition of the inverse of a matrix, and that's very important. And again, because we know that matrices really represent functions, I'm basically talking about an inverse function, right? So when one function does something, there's a function that goes the other way, and what that would mean. Right? So I'm talking about a function that's going to undo whatever A did. So A did something, B undoes it. It means it gives you back the original identity of the guy you plugged in. So this is called the inverse of a matrix. And I mentioned the phrase, so it's called invertible or non-singular. So next time I'll tell you how to find these. There are two main ways to compute inverses. There's a row reduction way and another way, but I won't have time to show you those here. So what I'm going to do is I'm going to introduce a device that's going to allow us to compute inverses, and then we end there. We're going to look at things called elementary matrices. Definition. A matrix E is called elementary matrix if it is obtained by performing a single row operation on an identity matrix. Okay, so take an identity matrix, do a row operation on it, could be a type 1, a type 2, a type 3, any operation you want, and you get this new matrix. This new matrix is called an elementary matrix. It's a matrix that when you perform any row operation on an identity, you get this matrix. Example. E equals is elementary. Since if you start with I2, which is 1, 0, 0, 1, and then what you do is take row 1 plus 2 row 2, which is a type 3 operation, that gives you 1, 2, 0, 1, which is E. So notice that this is the guy that I obtain by multiplying the second row by 2 and adding it to the first row. Okay? So this is an elementary matrix. It's a 2 by 2 elementary matrix. There are an infinite number of them. You can perform any operation you want. Here's the cool thing. I'm going to illustrate with this same matrix. Let's say I took, let A equal, say, 1, 2, 3, 4. And what I'm going to do now is I'm going to define E times A. So I'm going to have 1, 2, 0, 1 times 1, 2, 3, 4. Okay. Let's remember how to do matrix multiplication. What is this going to be? It's going to be a 2 by 2 because this is a 2 by 2, that's a 2 by 2. So they can multiply, the result is going to be a 2 by 2. What's it going to be? First row.
1 times 1 plus 2 times 3.
1 times 1 plus 2 times 3.
1 times 2 plus 2 times 4.
1 times 2 plus 2 times 4. 0 times 1 plus 1 times 3. 0 times 2 plus 1 times 4. What is that?
7,
7.
8. Oh no, 7.
10.
This is 10. This is
3.
3. And 4. Right? Do you notice anything about that matrix? Don't notice anything. Too tired to notice.
It maintained the bottom row.
It maintained the bottom row. Can you tell me something about the top row? So the bottom row stayed the same. Sure. What happened to the top row?
The upper left is the sum of the bottom row entries? Or is that just a coincidence?
What do you mean sum of the bottom row?
7 is equal to 3 plus 4? Or is that just a coincidence?
That's just a coincidence.
Okay.
The first row is twice the second row plus first row. First.
Right, if I took row 1 and added 2 times the second row, I would get 7 and 10. Right? How did I get this E that I mentioned? I took row 1 and added 2 times the second row. That's an elementary matrix. If I take that guy, multiply any other matrix, what does it do? It does the same row operation to that matrix that I did to the elementary matrix to create it, right? This is kind of the idea where we can talk about putting a property on our function that kind of colors its output, right? So by controlling the function itself, I can control what kind of outputs I get. But the nice thing about this is it now allows me to describe row operations in terms of matrix multiplication. So now I can talk about every time I did every time I had a matrix and I did a bunch of row operations to turn it to reduce or echelon form or whatever, I could think of that as just starting with a matrix and then multiplying by a bunch of elementary matrices in succession. Right? So doing n row operations is equivalent to multiplying by n elementary matrices. Right? And then using this idea of a row operation is equivalent to multiplication by an elementary matrix, we're going to prove a lot of nice things. And we're going to use that to figure out how to actually compute an inverse. Because ultimately, if I start with a matrix A and I do a bunch of row operations to create an identity matrix, what does that mean? Well, it means that A times a bunch of things ended up giving me the identity matrix. Right? Which means, in the event that these guys are invertible, which they are, which we'll prove next time, I can multiply on the right by all the inverses. And so I'll be able to say that A is just going to be En inverse times En minus 1 inverse all the way back to E1 inverse. And so, what is this guy going to be? This guy's just a bunch of matrices multiplied together, right? So it's just one other big matrix, call it B. Right? So I'm saying A times B is the identity matrix. What does that mean B is?
Inverse.
It's the actual inverse of A, right? So now, it's basically going to tell me I can find inverse by doing a bunch of row operations and interpreting it in this way, and I can just solve for the inverse whenever I get it. And that also tells you another equivalent condition. That means an inverse will exist precisely when my reducer echelon of a matrix gives me the identity. Because that means this kind of thing happens. By the way, that means, what's the determinant of this guy? The identity. 1, right? Now remember how row operations affect the determinant, right? Switch them, it negates it. Multiply by a scalar, you just get the scalar times the determinant. In other words, the determinant of this is not 0, which means the determinant of that has to not be 0 as well. Because no row operation is going to give me a 0, a row of zeros. So that also gives me an equivalent condition. If the determinant of this is not 0, then this is possible. Once this is possible, it has an inverse. Once this has an inverse, I can compute it. Right? And it's all going to tie together. Yeah?
So long as the determinant is not 0.
So as long as the determinant is not 0, it will have an inverse. So not all square matrices have inverses. The ones that have non-zero determinants have inverses. And we're going to prove that all next time, and we're going to use elementary matrices as our crutch. So we'll stop there. Pick up with inverses tomorrow.